All right, welcome to the SoDa Social Data Science Center Symposium at the University of Maryland. This webinar is being recorded and will be made available on the SoDa website next week. We will have time for questions and comments at the end of the presentation. I will be moderating the Q&A, and please use the Q&A feature at any time during the symposium to write in your questions. We also have some interactive questions where we actually look for answers from you. Those you can feel free to use the chat option. So we make full use of all the tech tools available. This presentation or this symposium today is a result of a class on data literacy and evidence building. The focus of today's webinar is on dealing with missing data in education and workforce analysis. And I do want to, before the presenters start, just briefly share with you the context of this particular class. And to do so, I'm going to show you the class website, and I invite you to look yourself. This way you can already all test the chat feature if it's working. At the class website material, we have last fall ran a course on data literacy and evidence building. And when I say we, then I'm talking about a collaboration between the Wagner School at New York University, Accenture, the University of Maryland, KY Stats, that's the Statistical Office of Kentucky, and the Coleridge Initiative. This program had a lot of different aspects, but one of its unique features is that program participants worked with synthetic data out of Kentucky Stats. So we'll hear more about these data sets in a moment. The unique feature of those data sets is also that these are administrative records as they come in the wild, meaning they do have missing data issues. And for all of you who worked hands-on on data, some of these problems will sound familiar. And we decided to create this bird of a feather meeting so that all of us here interested in missing data topics have the chance to, review what the issues were for those that were class participants, and for those that didn't participate in the class have a chance to join us in the thinking. I do want to introduce the various speakers that are contributing today. The first one will be Caro Hensch. She's a lecturer at Ludwig Maximilians University in Munich, where she teaches the Introduction to Statistics and contributes to various projects at the chair of Statistics and Data Science in the Social Science and Humanities. Their specialty is synthetic data, missing data. So that's why we pulled her into this project. Our second speaker is Tian Liu. She's a research scientist in the John Glenn College of Public Affairs at The Ohio State University. Tian's expertise are in the areas of policy analysis and evaluation, social policy, regional and urban economics, and policy and governance. And our third speaker is Angela Tombari. She's a senior research analyst and chief methodologist at Kentucky Center for Statistics. Angie has a background in psychometrics and currently focuses on developing metrics and common data models, as well as an understanding for the teacher workforce in Kentucky. So without further ado, I turn it over to you, Caro, to give us the first set of input. And while you put up your slides, for everyone to know, we are having these three presentations. Caro will actually present two models because Yang Juren, who was a speaker initially, got ill. And Caro will, after her presentation, also show us practical Jupyter Notebooks on how to do these things. But each of the different presentation segments will be followed by plenty of room for discussion and questions. So please don't hold back, put them in the Q&A, and then when time comes, we'll just allow you to unmute, or I can read out your question, whatever you prefer. All right, Caro, take it away.
Great, thank you. Yeah, I'm Carolina Hensch, and some of you, if you were part of the executive class, you might remember me because I worked with Angie on the synthetic data for the class. And when I'm not working on synthetic data, I really like to tackle missing data. And I will give you a small introduction today on the consequences of missing data, on different types of missing data, and then, of course, also talk a little bit about the methods to tackle missing data and the various pros and cons of different approaches. And missing data is a really common challenge in data analysis. And I'm really sure that if you are working hands-on with data, you will probably have encountered missing data in some form or another. And we would love this to be a little bit interactive. So please feel free to put in the chat your examples, maybe one occurrence where missing data was really annoying, made analyses really complicated, or where you just notice missing data. So please feel free to post your examples in the chat. And while you're doing this, I will talk a little bit about a few typical examples. And missing data can look quite differently. What I'm talking mostly about today is item non-response, so cases like on the right where we have several variables and a lot of different units. And for some units, some variable values are missing. So it's not that a variable is completely missing or persons are completely missing, but the case where some people, for example, didn't like to answer certain survey questions because they found them sensitive, for example. So they do not want to disclose their income or, for example, alcohol consumption, but they are fine with answering questions about their sociodemographics, for example, or other attitudes questions, for example. But for some questions, they feel like, no, I don't want to answer this. And then, of course, you have missing values regarding those questions. Another typical example are, for example, medical trials where some participants might drop out after a time because they do not want to participate in a trial anymore. So we only have data available for some time points or for some time for some kinds of examinations. Or a third example, in some panel surveys, for example, we even plan to not ask every respondent every survey question because we might be afraid that they get bored, that they drop off. So we ask different subsets of questions to different respondents. So we, in a way, we plan missing data to prevent survey fatigue. And I'm sure that you have examples from your work, from the data sets that you are working with. And and one common way of dealing with these missing data is to simply say, okay, hey, I will do a complete case analysis in the following. So I will simply delete any records with missing values and the variables that I will need for my, I don't know, estimation of means or variances, or maybe I want to do a regression of some type. And I just use the ones where all the data, all the variables that I need are available. And this is this is of course an easy and quick fix, and this is something that is often also included in statistical software. So, for example, if you run a regression in R, for example, you might often see the notice, okay, I don't know, 10 observations were deleted because of missing values, or a similar warning message. And this, as I said, this is quick and easy, and it might not be harmful for a lot of different analyses. So if there's, for example, very few missing values, this might be okay to do. Or in general, there are some cases where it won't harm. But in general, it will probably hurt us because we will, of course, very much reduce our sample size. So, for example, for our little table on the right, we would only have the first observation left because the second and the third observation have each a value missing in Y and Z. So that's often not a good solution because our standard error estimates might go way up. In general, our estimations will suffer from this reduced sample size. And of course, or you can probably imagine under some circumstances, it will even introduce bias in the analysis results. And we will now take a closer look at different types of missingness, because some lead to bias in estimates typically, and some don't. And I will go through 3 different types. And to make this more understandable, I will use an example in the following. So we might want to estimate income, the income of recent graduates, but we have different types of missingness here, some different scenarios where missing data might happen, and the consequences of this missing data are different for these 3 types. And in a way, we will now think about the mechanism. So we will think about the way how this missingness happened. And this will also be important when we look about strategies on how to deal with this missingness. So our study in mind is income estimates of recent graduates from universities, for example. And in the first, we have the first scenario is that we have some missingness that is what we call missing completely at random. What does that mean? It means that the missing data does not differ systematically from the observed data. And what could that mean? What is a scenario where we have missing completely at random data? Let's think of our study. So we are interested in income levels and the income among graduates, and we have a data set or records compiled on a computer, and then we have a malfunction which affects completely randomly certain persons, certain files on this computer, and we just lose a subset of our data on the recent graduates. There's no pattern or anything to it. It's a completely weird malfunction. Maybe 20% of our records get deleted. And when you then think about something like, for example, a mean estimate and the standard error associated with it, you can probably easily see that, of course, we have increased variability concerning this mean estimate, but we won't have any bias in this case. So since the deletion of the files happens completely randomly, at least in this case, we don't have a problem with bias in our estimates. But you can probably already see from this example, it's kind of unlikely that we usually have missing completely at random data, because usually it's not a completely random pattern, like with a computer malfunction, but instead we typically have something what we call missing at random. And these terms that I use here are very established, but sometimes also a little bit confusing. And I would encourage you to rather keep those scenarios in mind, at least for this session. And then you can go back and maybe look at these terms again. But something we usually use, we say, okay, the data are missing at random. And this means that the occurrence of the missing data is associated with the data that is observed, but not with the data that is missing. And we will look at an example to make this better understandable. So again, we are still interested in income. We might get data from another state or something, so we will do another study. But there we notice that graduates from education programs, so people who want to be teachers, they are more likely not to provide their income. And from the data, we know for each graduate which major they took in college. So we know, okay, those are education graduates, but they don't give us, a lot of them don't give us their income. So the missing, or the likelihood of the missing data is here related to something that we did observe. So we have the major for every graduate. And this is a good thing. And at the same time, it's not directly related to the unobserved data, so to the actual income. So the missingness depends on something we have observed, the major, for example, and we will make use of that fact. Great. So, and I mentioned, okay, there are 3 cases or 3 types. And since I emphasized that in the previous case, so the missing at random case, the missingness is dependent on the observed data. Of course, now we have also the case where it is the occurrence of the missing data is linked directly to the data that is not observed, that is missing. So again, we get another data set from another state. And there we unfortunately have the scenario that graduates from higher income brackets, that they are likely not to respond to this income question. And that the missingness is directly dependent on the income level that the person has. So it's not linked to the majors, but instead directly to the unobserved values of the person in that case. And this is the most difficult case. Fortunately, we usually can assume that the missing at random assumption is reasonable. I will talk more about this in a second. But yeah, just keep in mind, it can happen that your missingness is depending directly on the missing value itself, and then everything gets a little complicated. And so I already said, okay, so in the missing at random case, so the case where the missingness is dependent on something that we have observed, we have many tools available. In the missing not at random case, it's a little bit more difficult. And now, of course, it would be great to know, okay, if we have a data set with missing data at hand, it would be great to know if it's missing completely at random scenario, or missing at random, or missing not at random scenario, of course. But unfortunately, we cannot, there's no test to determine whether we have a missing at random or missing not at random situation. We can try to evaluate this in regards of whether the missing at random assumption seems plausible in a case, but since the data that we would need to test the missing not at random versus missing at random assumption is actually not observed, we also cannot use it for a test because we don't have it. That's the whole point. So this is a really, really difficult part here. And in the following, we will assume that we have missing at random missingness, because this makes our job a little easier, and it is also often plausible with the data sets that we have in social science or in official statistics. So with the assumption of missing at random in the back of our head, we can now look at a few methods for dealing with missing data. And what we will look here at here is imputation. So the idea is that we have this data set with some pieces missing. Someone took a byte, and we want to fill this up in a way, of course, that we can run efficient analyses, that we get low standard errors, that our analyses are unbiased. And we now have to think about a way in which we can do that. And this is not a new problem, since missing data is everywhere. People already in the 50s and 40s thought about ways of dealing with this data. And one of the most common approaches back then, but maybe even today, is to fill in, to impute the mean or the median or the mode that we get when we estimate those quantities with the observed data. So, for example, for the variable y here, we estimate the mean of y with the first and the third observation, and then from that we fill in the gap in for the second observation. Or for the variable z, we take here the mode from the first two observations. And this is also an easy way of doing this. And if you have missing completely at random data, so for example, our computer malfunction scenario, this will lead to mean estimates, of course, calculated with the whole data set that are, of course, unbiased. So the mean of the observed values is not different to the mean of the missing data, will only vary slightly. But you can probably already imagine, so the mean might be fine in the missing completely at random case. Using the mode might also be fine. But if we then move from point estimates to variance estimates, this already gets a little difficult, because if we just impute the mean every time we have a missing value, of course our variance estimate from the whole data set, where we use the observed values and the imputed mean values, will be totally off. We will vastly underestimate the variance. And similarly, we will run into problems with, for example, regression models. So there, our estimates, if we include these variables into analysis, will be off. And this breaks it down even more if we have, for example, missing at random data. There already our point estimates, like means, for example, will be biased if we simply use the mean value for the observed values. So easy to do, but this will probably only work in very few scenarios where you are only interested in point estimates, you have missing completely at random data, and you don't worry about variance. And people noticed this early on, and of course had some other tools available. So the next idea that came up was to use something like a regression for imputation. So you estimate, for example, the regression of y on x and z here, and for the missing values, you simply predict the value, and then impute it, fill in this value, the predicted value, in your cells with missing data. And this is all fine. Again, if you look, for example, at mean values, or if you look at point estimates in a lot of cases. But again, if you now imagine the data that you imputed, and for example, a scatter plot of two numeric variables, the imputed values will all lie exactly on the regression line. And again, we will have problems with variance estimation, especially, for example, of course, for estimates regression coefficient estimates, and we still underestimate the variation that would be there had we observed the original values. So this is still not ideal, and the next step was to think what we need to add to make the distribution of the imputed values even more similar to the observed values. And the next step is to realize that imputation is not prediction, so it's not about predicting a perfect value or predicting the best value, but instead to get a distribution of values that closely mirrors the original ones. So, and I see that I'm already taking too much time, so I'm jumping ahead a little bit to the solution that were developed. And one thing that we do when we use single or multiple imputation is to add to the prediction based on some other variables appropriate noise, so that the values are spread around the regression line, for example. And we do not only add noise because we know that the values will scatter around this regression line, but we also think about the fact that this prediction model that we estimate is also only estimated from a sample. So we have to also think about adding a little parameter uncertainty to this model. So a very Bayesian way of thinking. And these steps are all really great, and they already improve imputations by a lot. But back in the 70s, when people were trying this out, in simulations, they still noted that for estimates calculated from the whole data set, there was still some error. So the confidence intervals were too small, the standard errors, of course, were too small, and there was something missing. And the thing that is still not ideal is that when we take the data set and analyze it as if it were a completely observed data set, is that we forget that we included that these imputed values are not observed values. So we are not treating them right. And then when this was noticed, there was a statistician called Don Rubin, and he had a pretty simple and theoretically very well-founded idea. And this was to impute not only once with this process of prediction and noise and parameter uncertainty, but several times. And this is why we call this multiple imputation, because we do this process of imputing by creating a prediction, adding noise, adding some noise for the parameter uncertainty, not only once, but several times, typically 5 or 10 times. So for every observation that has missing data, we impute the values multiple times. So the data sets that are filled in, they will vary a little bit from each other. And now we have several data sets, and this was this might sound weird, and I think it was even weirder back in the day as a thought. So how we have several data sets, so how do we get to one overall mean estimate, to one all regression model? What do we do? And what is done is that you do the statistical analysis that you're interested in on each of these imputed data set separately. So you treat each one as if it was an observed, completely observed data set. And then in a last step, you pool all the results according to some rules that we call Rubin's rules, because he developed them. And if you're interested in the mathematical proofs why this approach leads to correct standard errors, to correct confidence intervals, and so forth, I can only recommend the Carpenter and Kenwood multiple imputation book, where you have the proofs and the Bayesian idea discussed even more. Yeah. So to summarize, so the one approach that will lead to good analytical results, given that we have missing at random data, is this multiple imputation approach, where we take the missing data, we impute several times, we do the analysis that we are interested in, maybe getting a mean estimate or getting a regression model on each of these data sets separately, and then use some simple rules, taking means, adding variances according to specific rules, back together that we get one model, one mean estimate, one whatever we are interested in. And yeah, this works surprisingly in a lot of cases. It doesn't work well if we have missing not at random data, and I see Frauke telling me that my time is almost up. The multiple imputation approach works great in a lot of cases where we have missing at random data. So the case where, for example, the missingness grows depending on the education major that we have observed. It's not working well if we have missing not at random data and no good predictors of missingness and the variable that we are imputing. Then it will break down. But this, fortunately, a case that is not often, that does not occur often. Often we have good predictors of missingness of the variable we want to impute, and then we can use this approach. But if you have this missing not at random scenario, there are two things you might want to check out, which is the selection model by Heckman and the pattern mixture model, where Ruben again was involved. They will help you dealing with missing not at random data. For example, if data are truncated, then you might need to use something like this. But this is also the scope of a two-hour lecture. So just putting this up, putting some references up if you're interested in that. And for the rest, I think we can do a round of questions, because this was probably a lot. And afterwards, we can take a look at the notebook and see this more in practice with some syntactic data.
Excellent, Caro. Thank you very much for kicking us off with these beautiful slides. We have three people that already posted questions in the chat. Adam, Josh, and Lance, and I believe you all are in the process of getting promoted to be able to ask your question yourself. And so, Adam, since we can already see you here on the panel, if you want, please unmute yourself and share your comment or thought.
Sure. Am I coming through?
Yes, you are.
Okay, sorry, just in the office, which is a strange thing to say, that I don't know how that works, but I'm not in here often. Yeah, I was just saying that in the early part of the conversation where we were talking about, how do you deal with missingness? That was kind of the first initial question. And in my mind, when we got into the bit about, you could throw out records where the data doesn't look very complete. And it seemed like, you can throw out the X's, but you could also throw out the Y's. Right. So if you have mostly complete data across most of the variables you're interested in, but there's like one or two variables that are very incomplete or very inconsistent, you could perhaps throw out those variables if you don't think that they're terribly important to the analysis, and then have more X records available for what you're doing. So it was less a question and more just kind of opining on the methods. I think there was a question about, how are we approaching different things?
Yeah, this might make perfect sense if you are not dependent on the variable in your analysis and you have too little data to put up a good imputation model. then this might be wiser to build models around the
And
available
I
data.
love that comment, Adam, because and opining anyway, anytime. But I do think what you described there is something that can't be emphasized enough. That that it's really worthwhile looking at your data and understanding them as a whole, right? And not, you know, just because you would like them to be a certain way, analyze them as if they are, right? So looking also at columns rather than just rows, I think is very important. Yeah. So Josh, Holly, I see you up there too. Do you want to share your question, comment, thought, opinion?
I'm sure, and maybe this is probably a question that maybe Angie could address better later on, but it's when missingness comes not from measurement, but from policy or lack of guidance on implementation. How do you model that? And I think that's a lot of us when we deal with policy data, we're dealing with missingness that's a result of a political or administrative process. So
I'll just add, Josh, you totally are correct. That's going to show up in my slides.
Good. Then let's shelf this for after Angie talked. I too have some thoughts on that from my experience at the IIB in Nuremberg, the Institute for Employment Research. Lance, you had a whole bunch of questions. Do you want to unmute yourself and ask them directly?
Can you hear me?
Yes, we can.
Yeah, I'll just leave my comments in the chat. We all are very smart people, so just consider them for what they are.
Excellent.
I won't
All right.
comment any further. Thank you.
Okay, great. So maybe I can relay one of them. And I think to your point, Lance, we will be getting a little bit into how do we actually predict those values. That's what Caro is going to do right now. I haven't seen anyone else contribute to the chat. So Caro, maybe this is a good moment to jump into the notebooks and then do exactly that, what Lance was asking. How do we do it?
Yes, let me jump to the notebook. Okay, so I believe that this notebook will also be made available on the website, and I see people nodding. So there's a lot in here, and I will mainly talk about the results and what we see here. So the executive class people have a little bit of an advantage here because we use again the syntactic data. And if you're not familiar with the syntactic data, we use records from wages and education data in Kentucky to create a synthetic data set that is similar to data that we see in at KY Stats. And for this notebook, we will just use a little bit of the data available. So there are a lot of variables. Here you can see some of them. And maybe Lance, you could unmute yourself. We can still hear you a little bit. Would be great. Yeah. So what you can see here is the data that we have available in the syntactic data, and we will only use 3 of them here: gender, year 6, and year 7 earnings for a little demonstration of how imputation works. So in the first part here, we set up the data set. So we only use gender and year 6 and year 7 earnings. So year 6 after starting a degree and year 7 after starting a degree. And we will first look at men in the data set. And there we, as creators of this notebook, we delete some of the year 7 earnings that are in there. And we do this based on their year 6 earnings. So if they are below the some percentile, they have a higher probability of missing data. So low income workers are more likely to have incomplete data here. One could think of a reason like, for example, they relocate more often. So in our case, if they have low earnings in year 6, they might move somewhere else or don't provide their income in year 7 for other reasons. But the important thing is here that the missingness that we model here is dependent on year 6 earnings, which we have observed completely. And in year 7, we have some missing depending on that other variable. So a missing at random scenario. And of course, missing the year 6 earnings are of course also a very good predictor for year 7 earnings. So this will make our life easier in the following. And for the women, we do a separate data set, which we will see at the end. And there we have a missing not at random scenario. So the missingness is directly dependent on the value of the year 7 earnings itself. So, and now, so we did this preparation to just show you the imputation methods a little bit. And there's a lot of code, which we will not go through here. But what is important that we will first try the first approach that I mentioned, the unconditional mean imputation. So just estimating the mean from the observed values in year 7 earnings and using this for the persons with missing year 7 earnings. And this is done in the code here. So we impute all this and then we create a plot of observed and imputed data. And this is actually a plot or something that you might want to inspect after imputing values. So a lot of imputation packages offers some plot function like this, where you can compare your observed here in blue and the imputed data here in red. And yeah, you can immediately see that something is off here. If we think about the imputed values, we might hope for values that look similar to the observed values here, at least in general. They shouldn't have a completely different form than the ones we see for the observed values. And if you look at this, we have this red line here, and it's a line because we used the same value for every person with a missing year 7 earnings. So we have year 6 earnings on the x-axis and year 7 earnings on the y-axis. And for the observed data, we see a strong correlation here, of course. But for the imputed data, this is of course completely destroyed because we just used the mean of the observed year 7 earnings for every person with a missing value. So this is pretty bad. And of course, we can also again think of what will this do with the mean estimate of year 7 earnings, and what will it do with the variance estimation. This will be vastly underestimated. And of course, also for regression estimation, this is of course also terrible because the relation between year 6 and year 7 earnings gets completely destroyed here. So lots of problems which we can see in this plot. What you will also find in this notebook is also a comparison of the full data set before we artificially, in this case, deleted some values to set them missing. Then our little simulation, then the data set without these missing values. And for example, here you can see big differences in the estimated income between this full data set and the data set with only the complete cases. So as I mentioned, there's a huge bias if we just do complete case analysis in this case. And we see that mean imputation in this case does not help. We still have a biased mean, and the variance if we compare these three data sets, the full data set, the data set where we have some data missing, and then here with the missing data filled in with the mean, we see, okay, our variance estimate for year 7 earnings is completely off. It's way too low because we just imputed the mean here. So not really a surprise, but still a little devastating to see this these results. But we have some other tricks in our toolbox, and the next thing we can do is try, for example, conditional mean imputation or something like a regression imputation. So we might want to use some other information, like, for example, the year 6 earnings, to impute our missing values in year 7 earnings. And this is already an improvement. I will jump here to the results. And here in this case, we decided, okay, we will use the year 6 earnings a little more. So if a person earned less than, I think, 50,000 in year 6, we take the mean of the observed values from this group. So again, those who were in year 6 earned less than $50,000, and we estimate the mean for this subgroup and take it to impute the year 7 earnings here for the people who have missing values in year 7, but in year 6 were below $50,000. And then same, we only have 2 groups here. So we have another mean estimated from those in the higher income brackets in year 6, and then impute this in year 7 for the year 7 missing values. And of course, this is already a little better because we make a little bit use of this correlation that we have here between year 6 and year 7 earnings. So of course, this imputed value, these imputed values are a little bit closer to those, or are a little bit more similar to the distribution of the values before deletion. But still, yeah, pretty horrible. We can take a short look at the mean and variance estimates again. And here we can see, okay, we have again the full data set, the data set after deletion of the incomplete records, and then our now imputed values with this a little bit more sophisticated model. And we see, okay, this already helps with the mean estimate. So our mean estimate after conditional imputation looks better. The variance is still pretty bad. Of course, if we look at this, you will probably agree that this is not a realistic pattern. And so we might shy away from using this. And yeah, we have my favorite. We also have my favorite method, which is multiple imputation. And I have to admit that the implementation in Python is not as great as in, for example, R or SoDa. So in those languages, there are really great packages available. Here in Python, it doesn't have as many functionalities as functions and possibilities as in R and SoDa, but we can still make it work here. And again, jumping to our plot here, and what we can see here are again the imputed and the observed values, and you probably notice the lines are gone, and instead we have again scattered plots here that look kind of similar to the observed values. You might notice this weird change of pattern again around 50,000. This is because we set up the missingness mechanism in that way. So if you're below these $50,000, you have a much higher chance of missingness than if you're above that threshold. So that's why we see this hard cut here. In reality, this would probably be less distinct here. But yeah, this is what it should look like. So you should have plausible values after imputation. And if you use the functions available to then do this 5 times, combine the estimates, you can get, again, overall estimates for mean, for variance, and so on. Just a little quick look at the results here, and we can, so I think this is only from, no, this is, yeah, this is correctly. So after using Rubin's rules, we can now look at the mean, for example, here, and this looks again good. And also the variance estimation is now working well in our case here. So great news. If we have good predictors of missingness and the missing data itself. So in a lot of cases, we will simply, if we have a data set of maybe like 30 variables or so, we might just use all the variables available to predict our variable with the missing values. It won't harm to include those additional all the 30 variables or whatever you have available. If you have more, you have to take a little bit more care in building your missingness model, so including strong predictors of the missingness, and the variable to be imputed is always a good choice to include the variables that you want to use in your substantive model, so the model that you are interested in estimating after imputation is a good idea. And there are also some guidelines out there on which variables to include in that case. In general, though, with missing at random data, you are set with multiple imputation. Problem is if you have missing not at random data, and I also include a little example here with the women's data set, where we use the missing not at random missingness mechanism. And you can then check out what using year 6 earnings to predict the year 7 earnings, how much this is helping or not. It corrects most of the bias, but not all. And this is also typical to be expected in such a case. And yeah, that's that. As I said, lots of code. If you're interested in that, also an implementation with the mice function in Python. And yeah, just a little intro to missing data and multiple imputation.
Great, thank you, Caro. And inviting again everybody here to post questions in the Q&A or in the chat, or raise your hand so we can unmute you. And Jan, Angie, if you want to chime in with anything to the code books, please do so. There was one question, Caro, from Ross, wondering, given about the linear nature of your scales, the X and the Y axis, given that income is often so skewed. And I see, Ross, you're up here on stage, so maybe you want to ask it yourself.
Oh, I just remarked that I noticed that the X and Y axes of income was scaled linearly, but in real life data sets, the income variable tends to vary exponentially, not linearly. So wouldn't a log-log scatter plot work better? Of course, I don't know how the synthetic data was constructed. If it assumed income as a linear variable, then that would be a different situation.
Yeah, we did this also to offer greater privacy protection. So that's another factor here. But in general, I completely agree with you. A log-log scale would also make perfect sense. And this is only due to my very limited Python knowledge that I used yesterday to throw in this extra plot. But yeah, it would make perfect sense. And when you create your imputation model, it's of course also possible to transform these variables to log or whatever you want to use. So just like with any other regression model, you have a lot of freedoms that you can explore. Yeah.
Thank you.
Great. Caro, one more question that came up here from and there you are. And you mentioned that you have limited Python knowledge. Do you have those codebooks in a different language, in R or something rather?
I don't have this codebook in R available, but the materials from Stefan Bühren are excellent. And if you're using R or SoDa, I would, and especially R, I would definitely recommend his free books online. He has a book, Multiple Imputation, with lots of examples in R. It's a wonderful guideline, and I can definitely recommend this one.
Great. Great. We have another comment from Lance. He is saying an unemployed new business graduate is prone to think that the unemployment rate is 100%, not based on their training, but based on their disappointing experience. Unfair zero and low wages are agonizing. An unemployed new business graduate is not a happy respondent. So bottom line, biased responses, right? In small businesses, but other cases too. How do you deal with that in practice?
Well, if we have biased values that we use for imputation, we will of course transfer this bias also to the imputed values, of course. But you can treat such measurement errors also as a type of missingness problem, so that you try to impute a corrected variable. So yeah, there again, you can make use of multiple imputation or imputation in general. So again, the answer is multiple imputation.
Angie, Tian, any response from you guys?
So I was just going to say, it seemed like a really great question, because as far as that was one of the things that's always I worry about, is that if there is already something baked in, or if I have not used all of the correct variables within here, there is the possibility of making it worse by virtue of going through this scenario. So it's a great question. I don't think it's been solved, which is part of why it's such a great question.
Absolutely.
Yes, I definitely agree, and I can very much understand the fear of making things work with multiple imputation. And I very much relate to that. I then just think about the other case using maybe something like complete cases analysis, and then I'm usually not happy either. So, and then I at least try to explore other options.
Yeah. Great. All right, let's continue with Tian, and then followed by Angie, and then we can have another round of discussion. Go ahead, Tian.
Oh, do we need a 5 minutes break in the middle?
I think we're good to continue.
Okay, cool.
Go ahead.
Okay, so thank you everyone. And today I'm going to talk about the types of missingness in administrative data. So I will just start with an example from the syntactic data, and we'll look at the results, and also just to think about what could be the potential missingness in this specific data set. And then I will show you how the results look like if I apply the 3 different methodologies that are shown in the notebook. And also at the end, I will just talk about some of the examples from my own work experience. So first, the syntactic data example. So let's just assume that academic advisors want to have some descriptive statistics just so that they can advise what their students, like what degree level or what types of college they should go to. So assume that you are a data analyst and you have access to the 2015 syntactic cohort data, and the outcome measure that is available to you are the inflation adjusted year 7 earnings. So this means 7 years after first enter college as degree pursuing student. And you have those data for associates and also bachelor's degree degree earners. And the underlying data sets are the syntactic, higher education, and UI wage records. And of course, you can argue that there might be better outcome measures available out there, but here I would just use the year 7 earnings as an example here. So this might be the results you have already seen in the training. So basically, if we just use the data that is not missing for the 2015 cohorts who have a bachelor's degree or an associate's degree, the major conclusion we can really draw from this visualization is that we may think that associate's degree holders and bachelor's degree holders, at least at the 7 years, at year 7, they have very similar earnings. Or we can just say that they have very similar earnings at the beginning of their career. However, this is counterintuitive, or at least different from the results that we can see from other data sources. So for example, if we look at the results from National Center for Education Statistics, or the Bureau of Labor Statistics, we always see outcomes like people with higher educational attainment, they should have higher average earnings. So even if the data sources or specific measures or the underlying populations are different, but we typically just think that higher education should be translated into higher average earnings. So what could be the potential? So what could be the potential reasons? So again, you can argue that this outcome measure may not be the most appropriate, but let's just focus on the missingness aspect for this specific example. So first of all, one thing you can do is really to inspect the missing rate in your data. So what we can see here is that the first 2 bars shows the missing rate for bachelor's and associate's degree holders for the full sample. And you can see that the missing rate for bachelor degree holders is much higher than the missing rate for associate degree holders. It is even greater than 50%. Or in other words, if we call this a so-called in-state employment rate, how can bachelor degree holders have lower unemployment rate than associate degree holders? And this is still different from what we usually see in other data sources. And if you further break down this data by subgroups, you can see that at least across those subgroups that are available to us in the data, across all subgroups, bachelor degree holders have higher missing rates in year 7 earnings. And another thing that is worth to mention is that the difference in year 7 earnings missing rate between bachelor's and the associate's degree holders is relatively larger for the non-underrepresented minority group and also the male group. And this typically to be the 2 groups that tend to have higher earnings. So given like those patterns we observed in the data, and if we go back to think about the data that we're using, so what could be the potential missingness, and what could be the method that we can use to deal with those issues? So first of all, if we take a look at where we get this earnings data from, it is from the UI wage records. And typically, if we cannot find a person's earnings in the UI wage records, this person could actually be unemployed, or the person could have moved out of state, or have a non-UI covered jobs, such as federal jobs, self-employed, or contractor workers. And another case is that even if the person still stayed in Kentucky and didn't have any non-UI covered jobs, this person may not absolutely be unemployed. The person could be out of labor force. So if a person does not have earnings records, the person could either just still looking for jobs or not looking for jobs because of childcare responsibilities or other reasons, or the person may continue education and choose not to work and study at the same time. And also another thing that is worth to think about is that even if you can see a person has records in the Kentucky UI wage records, so what if the record you are seeing is that their earning is $1 during a specific quarter? Could that be a data processing issue, or could that be the actual earnings for that person? So in addition to the missingness in the earnings data we also want to think about what could be the potential missingness in the original sample that we're looking at, which is the higher education data from where we get the bachelor's and associate's degree holders. So first of all, the private college. So this is not a typical issue for the Kentucky data because it has both private and public colleges, but it's not always true for other states. So for example, in Ohio, the higher education data only includes public college information. So if this is the case in your state, then you may think about like, what about the private schools, college students? Is it likely that for students who get degrees from private college, do their bachelor degree holders have higher earnings than associate's degree holders? Can that explain the discrepancy from your results and the public and the other public website results? And another thing is that this still relate to your underlying sample choice. Again, if you only care about students who acquire degrees from Kentucky, then it's fine to use the data. However, what if students transfer to college to other states or even overseas and receive degrees from those out-of-state or international post-secondary institutions? If your focus is really anybody who ever attended college in Kentucky, then essentially you would not have this group of people in your data. And of course, there are essentially other missing information that you don't have in the higher education data at all. So for example, some of those online degrees, certificates, or credentials that are not covered by those public or private school records, and also apprenticeship or vocational training programs. So for example, students from some majors, maybe it's very likely for them to receive additional trainings in those vocational training programs. And could that explain some of those, could that explain that they are relatively high starting earnings? And finally, there is always data processing or documenting issues. Like different institutions, they may have small differences when they document those degree information, or sometimes when some of those measures could change, like for example, the major fields like the zip code, it could change over time, and some institutions may adopt the new zip codes immediately, and some institutions may have a lag. So when you're analyzing those data, there may always be a small discrepancies like this. So anyways, so after we think through all those different, potential missingness in our data, we can probably, now we can just use some of those simple imputation methods that Carol just showed to us and apply those methods to this in this specific example, and to see how our results might change. So as you can see that the first two bars showed the original results, and of course with unconditional mean. Essentially for this simple descriptive analysis, even if you apply the unconditional mean imputation, the results will not change much. Same for the conditional mean imputation. And in terms of the multiple imputation, the results did improve to some extent. We did see that now we can see some level of difference between earnings of bachelor's degree holders and associate's degree holders. However, the difference is really not as large as we can see in other data sources. So with those results, I think this is consistent with what Carol just mentioned about those different types of missingness. It's very unlikely that in this case, given the discussion earlier, it's very unlikely that this is missing completely at random, because we can see that there are certainly some systematic bias, systematically missingness in our data. And in terms of whether it's missing at random or missing not at random. So given the little bit of correction in the data, I would say it's probably still a mix, but unfortunately, it's very hard to differentiate these two types of missingness. So next, I would just like to share a few examples about missingness in data in my own work. So the first example are the missing industry information in Ohio UI claims data. So typically, the data is relatively complete. However, at the beginning of the pandemic, the industry information was missing for a large proportion of UI claimants. And this is because this group of UI claimants, if they lost their jobs because of the pandemic, we didn't really document their separating employer or separating employer industry information. And as you can envision that if we want to conduct industry level analysis, the missingness in the industry information is very likely to be biased, because the pandemic hit a few industries particularly hard, like accommodation and food services, and also manufacturing industries. So the way we deal with this missingness is that we linked the UI claims data with both UI wages and also QCEW, and use the quarter of their employment prior to they filed UI claims to impute the missing industry information. And the second example is what we talked before, like what if students transfer to other schools, to schools that are out of state, or to private schools, if private school information is not part of your state's higher education data set. So a good resource is National Student Clearinghouse data. It includes both private and public, as well as in-state and out-of-state college enrollment and graduation data. And in fact, NSC data include the coverage is about 96 to 97%. So some private college may opt out, or some students may choose to opt out, but the overall coverage is very high. So however, when we use, so in a project that I've been involved in, so when we want to use this data to look at like what percentage of students actually transferred out of state or transferred to private college, what are their outcomes? We do find that the results was not what we expected. We do see like a lower percentage of people enrolled in private college than the results we can find on other public websites. And when we trace back to the underlying reasons, we find that actually when the state agency, so basically the way we can get this data is that the state agency will send a list of student IDs to National Student Clearinghouse, and they will return a set of data for this specific list of students. And then we find that because the state agency, because they are only interested in follow-up two-year public college enrollees. So actually only this group of students were included in the data that we're using. And a third example is about linking K-12 to workforce data. So this is a typical problem that usually in K-12 data, we have student identifiers, but for workforce data, we rely on social security numbers to link people. And it's very hard to really link student identifiers with social security number. So so here we used a probabilistic matching method, and we link students with supplemental data sets and create a crosswalk between student IDs and the workforce data. So however, this actually leads to, so this allows us to observe a lot of students' outcomes. However, this again, even if we are able to link students' data with workforce data, there could still be potential problems, like the matching rate is not always 100%. And we just have to always keep in mind that even with supplemental data, there are still additional missingness issues. So for example, we do observe that students from some groups have lower matching rates, such as some minority groups or the economically disadvantaged groups. And the last example is about missing identifiers and some missing fields in vocational training data that is caused by change in administration. So in Ohio, prior to 2014, those information were relatively complete in the data. However, administration of the vocational training programs changed in 2014. And some of those key identifiers and some fields were no longer required. So the administration no longer require participants to report the key identifiers and other fields. So while there has been an improvement over time in the recent years, however, those missing data is very hard to recover. So what should we do when we are dealing with data? So of course, first of all, is to proactively thinking about the missingness in your data. And after you identify the missingness, so what are some of the recommendations from us for you to deal with those missingness? So first of all, of course, whenever you can find additional data source to supplement your current data, that would be the ideal case. Like I mentioned before, if you can supplement it with the UI-Wage records and QCW to get out of state employment, that would be ideal. And another case is just that if you even if you cannot get out of state data, it would be ideal to at least check with some of the in-state data, but with a larger coverage. So for example, the Bureau of Motor Vehicle Data is a good resource for you to check whether people move out of state. And again, the National Student Clearinghouse data is good for you to check if a student enrolled in private or out of college or out of state colleges. But of course, again, keep in mind that those additional data sources could have their own limitations. And also, if you do not have additional data sources, at least try to compare your results with statistics from other data sources, such as the survey data, just so that you can get a sense about what could be the potential bias in your final results. After you think through the potential missingness and also bias in your data, you want to understand the underlying data generating process. Again, is it caused by a change in administration, or is it caused by the data pooling process, or is it just the data coverage issues? And then choose the appropriate imputation method. So as Karen mentioned, so you want to think about how likely is the missingness be missing completely at random, missing at random, or missing not at random. A lot of the times it's very likely to be missing not at random. So even with the multiple imputation method, because your information is just limited to observe the data, it's just very hard to recover those unobserved data. So it may require additional, more advanced imputation methods. And finally, if all of those tools are not available, I think at this point, what would be great to do is to at least document the potential missingness in your data. So for example, when you report the results, it'd be great to address the coverage and the missingness in your data, or at least report the missing rate in some of the key fields. So that's the end of my presentation.
Fantastic. This is wonderful. I so much information in there, and we saw a little side chat here going on between Adam and Angie on the $1 wage values. With an insight, Angie, do you just want to briefly summarize here your experience?
Oh, I'll pitch it over to Adam momentarily, but the $1 values in here have been something that have driven me crazy since pretty much when I started at KY Stats. And we do know there's a particular reason for the $0 values. And that one I got an explanation for, but one has always driven me crazy. And Adam offered a possible explanation, or one that's true for Texas, that I might want to look into here. Adam, do you mind sharing?
Yeah, so that was one of the things that I started seeing in the data when I got here. And so we were looking for reasons why somebody would do that, and why we would see this. And then we said, well, the answer is not to look at the records, the answer is to look at the submission. And so what we started doing was looking at the submissions with those records, and lo and behold, we found that in a lot of instances where that occurred, all the records but one would have $1 on them, and all the rest of the wages would be up on a single record. So basically, they just, for whatever reason, didn't feel like correctly reporting the data on an SSN level basis. And they would put $1 on, 40 people, and then, I don't know, whatever that would be, $1 million on everybody else. Which created another problem at the other end, obviously. And so we kind of tried to figure out what was going on there. And, the UI division doesn't, it's not to say they don't care, but they kind of don't care, right? They have the number they need to do UI taxes. And if on some miracle, one of those people files a claim that happens to include one of those records in the base period, because remember, the vast majority of records are never used in a UI claim, they can just correct it then, rather than going through the trouble of trying to get all the records collected. So their needs have been met. And so that's what we've been dealing with. And really kind of that lesson about going back and looking at the entire submission by an employer and not just relying on the SSN to individual wage match to analyze things. I mean, I think there's a lot to be learned from looking at the person and the employer and not just the person and the wage.
Absolutely. And this is what I loved so much about this class and also this session here, that you guys with the practical experience and the real knowledge about the data just have so much to add. And if you're just there as a statistician or a data scientist hopping from one project to the next, unlikely that you're gonna figure this out. So thank you. This is great. Any other questions for Tian? Russ, do you want to chime in or just for us to read here on the chat?
No, my chat text is fine. I was just citing another example of
Great.
bizarre examples.
Yeah. Now I do think that, this lesson learned can also be transported to other data sets that where a record sort of needs to be there. It's probably a UX interface that requires to enter something in order to move on. That's something that I've seen a lot. And we overlook that, I mean, as a service statistician, we think a ton about how to design a questionnaire so that people can like easily follow through. And in particular, you don't want to force people to give an answer to something because then they might answer stuff that's not true, right? And administrative record entries are often of a similar kind, right? But the folks who do program these systems, they don't know all possible cases, and then people get creative, right? If it doesn't fit, then they have to move on, and then we look at the data later on and we have no idea about the creativity, right? And so putting oneself into the shoes of those that are filling out these forms, I think can be very helpful. But to make sure we're not running out of time, Angie, I think I'm going to turn it over to you, and then we can open it up for a general discussion at the end. Does that sound good? Great.
All right. So a lot of what I am going to talk about is this same sort of component that was just brought up in these questions. Because I learned a lot about missing data once I started working here, and my alternative title was Lessons Learned After Grad School, but I shifted it over to Lessons Learned in the Workplace for the formal presentation. So we have all these technical terms we've been tossing around. I also, brief apology, my camera is at a place where I can't see my screen, so I know I'm going to be glancing that way. Please ignore that. So missing completely at random, you described this optimal condition, and I think, Lance, that one of the things you were having issues with was that it feels unlikely to ever occur. And so gold star, we want this to happen, assume it's not happening. And these side cases we've been talking about and that Adam's brought up, Ross has brought up, all of that is the key here. In general, if I'm working with administrative data, I assume it is missing very much, not at random. And so I'm going to walk you through just a couple different, first, how I think about it when I approach something funky in a data set, funky being the technical term. And then I'm going to talk about some of the ways that we approach it when we do have missingness, and we're trying to work with it without maybe having the time to do something like multiple imputation. So one of the first things that I did when I came to KY Stats was work with teacher data, which is why that got noted in my intro. And I had to figure out inexperienced teachers in the workplace. That was a question I was asked, so it seemed really simple. We have an experience variable. And the interesting thing here is that both sorts of these end missingness are going to show up in this. That with teachers, the first 2 years of data that I had, I found that it was completely blank in the experience. So it just wasn't reported. It was not related to anything else. It's just not collected at that time. But after that, when I started looking at the later data, the missingness within this variable was needed to be deconstructed into what exactly it was related to. So this is early in my career, and basically I started off by just trying to find missing values and looking at what do I have, and their teachers, blank years of experience, and contract days. There's a lot of other information that goes into this. But my first check was, are there missing values? And then I wanted to start to see if there are patterns to it because I assume a pattern. And I grouped by year, which is one of the things that I've learned that you should absolutely always do. And you really want to look at whatever level of granularity is true of the data collection process for what you're collecting. And this is an academic year report that we get. And when I looked at it over time, I found those first 2 years of complete missingness, and I was left with this import. I grouped by location because I thought maybe it's a data entry thing. Maybe some people are using it creatively. They have unique circumstances, and there were some patterns, but nothing that I could pinpoint from what I knew. And so ultimately, I started to think about looking at it in terms of longitudinal for these people. And so this is an example of what data could have looked like, but when I started to line it up and order it by person and year, that's when I started to notice some similarities in here where there was always at least a 1-year gap when I started seeing this missingness. I also saw that the years of experience were high. And what that led to was to me go and grab the technical documentation for how people are told to put this in, and also to add in additional pieces of information I knew to be related to retirement. So ultimately, what I found out was, yes, this is because people are retiring and they're coming back. And that meant I could safely assume that these people are probably not inexperienced, they're absolutely experienced. But the other interesting thing was in the later years, I no longer had nulls. And I knew people were coming back from retirement. So that led me to realize that they created a solution to this that was great for them and less good for me in terms of administrative data after you were out, because you're no longer acquiring experience for the Kentucky teacher retirement system. You've already retired. They just keep putting 0 in. So this is a case where once I understood what was happening, I was able to use a loop and come up with some sort of derived experience and figure out a flag for when someone could likely first retire. So in that case, I was able to find a number that matches pretty closely with the Kentucky teacher retirement system reports in terms of number of retirements. But a lot of times you cannot put it back together with the data that you have, or it might not be that simple. So I'm presenting a couple alternative solutions for the scenario in which you yourself cannot solve it immediately. And they're going to go in order from the simplest to the one that probably takes the most effort. So the first is contextualize it. And that's where Tian talked about adding in information about how much missingness. And we often deal with dashboards or very short reports. So I think about this in terms of something that's on display. And when I say I think about this, I really mean a lot of my fabulous coworkers think about this, because I am not the person who does any of these displays. But for an example, we've talked a lot about in-state only outcomes, Kentucky only post-secondary report. This is something that it was a flagship report. We've been doing it for years, which means the format you see it in now is a far cry from where it started. We've added things. And one of the big things that was a problem for institutions was different institutions bring in different amounts of students from out of state. And we also knew from the literature that out of state students were more likely to exit after getting their degree. So that became something that, without knowing the size of the out of state population, it was difficult to understand why an employment rate might tank and be completely unrelated to employment outcomes. So the first thing we did is actually on the right side of your page, which is adding in student origins. And that was suggested by our Council on Post-Secondary Education. They made most of these solutions and we implemented them. And so this way, when you select an institution, you could actually see what percentage of the students that they're in the recent year are coming in from out of state. And it gave you some idea. As we got more data, we were able to hit that second star on your left-hand side, which talks about the student origin, and we actually added that filter in. And that filter in was really to help our institutions that had a large out-of-state population. And then another thing that we ended up doing was making sure that we were super clear about the fact that this is employed in Kentucky. So that red box is highlighting. We have argued a lot about that simple terminology and whether we should include UI covered wages in there or not. The fact that it's only in a particular system, with the caveats that Tian has mentioned. So it's front and center in the tech notes. It is not on this page, but we do present on this a lot to educate people. So another thing that we have done is if maybe in this problem, we've talked about variables that are absolutely critical to the analysis. So if we're thinking about post-secondary employment outcomes and something is incredibly critical, you might actually end up changing the way you're asking the question. So your question is instead going to say, I really want to know the return on investment for all post-secondary students, but I need to be fairly confident that they stayed within the state. So I'm going to put a lot of restrictions on this. And I'm going to say, I end up talking about the return on investment of a group of students who is doing a very specific thing. So I think about it in terms of doing an experiment in the lab versus in the field. And we have more confidence in our results, but we are not confident that it generalizes to people outside of this. So this is taken from us looking, it's not overly important exactly what it is, but we wanted to follow high school graduates and say, okay, at what point kind of do they break even? And when do they start earning more? Because they've got an opportunity cost, they've got loans, all of those pieces. And this is done with our Council on Post-Secondary Education, fabulous partners that I mentioned. And we ended up having a lot of criteria to make sure we could be confident that if we were missing them, they weren't out of state, where Tian talked about getting the driver's license information. Know that for this, they needed to be employed or enrolled in every year that we were looking at to feel like if they were working a job covered by the UI system, we would have gotten the wages because they were here. And it's imperfect, but it helped us have a little bit more faith. The findings behave the way we expected. But what happens is, and there are a lot of other criteria we had to put in, it went from a high school graduating class of, 400 or 40 something thousand students down to about 10,000 people that we were following. So we have less than 25% of our original group. But we are fairly confident that for this group, this is what happened. So that is an option. And our final solution in terms of difficulty is going to be get more data. And that often involves a lot of MOUs and pieces of information around that. So I put it as the last option, but I want to have these caveats of, I think Tian mentioned, it has to be the right data. And so you really want to understand and have a good hypothesis on why you're measuring this data before you just go out getting data. And I'm going to show you a case of where it's been successful and where it's been unsuccessful in terms of getting a particular subset of data. And so this is more data, the partial fix. One of the things reported within our state is that people don't have enough STEM bachelor completers. And so when we look at our post-secondary feedback report, you would expect like, oh, maybe all of them are employed. Say we captured the whole universe because they can't find them. Well, no, we find the lowest employment rate out of our bachelor completers for those whose major group is in STEM. And so solution, more data, getting Ohio, Indiana, Tennessee, we can see how much that changes the picture. And in this case, the problem is probably not just the border states, because we've got more information across all of this. We know for everyone, it's somewhere between 11 and 18 percentage points more employment that we can pick up with these 3 additional states. But we're still low here. So they're either, maybe they're more likely to be self-employed or fall outside of the UI claims, or the labor markets we're competing with are just not that very local. Maybe it's a more global piece, which I think is very arguable. And we could imagine it being California, Silicon Valley, or Texas, with Austin being the new Silicon Valley, as well as a lot of other places. So this helps, but it doesn't solve our problem. And then, of course, we know, where does it work? It's the same idea of right now our outcome is employment and wages. So it's going to matter the labor markets. And our biggest issue is those places where it's very integrated and the border is artificial in terms of how people themselves are functioning. And so we have, this is an image from the commuting patterns report. It's giving us our living and working and showing that integrated nature. And we always highlight Northern Kentucky because that is part of that Cincinnati metropolitan statistical area. And this is the particular place that gathering that data is going to fix. And so we like to point out that it does, that you get over twice as much, your employment rate more than doubles here. And also that it becomes our Northern Kentucky University on our side of the river speaking as a Kentuckian, just on our side of the river, they have, I think, the highest, or if not, it's close employment rate once you add this in, because they have a very bustling labor market. You're likely to find employment, even if it's not the employment you want. So it makes perfect sense that in a place with a lot of jobs, you would have a high employment rate. And it does also work from the other direction in terms of, even though Ohio, like, they're doing something right because people don't want to leave, as far as we can tell, or maybe they just don't want to come to us, but that's okay. They tend to only have about an additional 3 percentage points of employment that's picked up across all categories, but there's variation here. So this is looking at the Cincinnati State Technical Community College, which is just on the other side of the river, the side that would generally be considered the nexus of the metropolitan statistical area. And they're picking up a lot more employment. So it is reflective on both sides, but this is a case where we knew what we thought was happening. It is what the institutions knew. It is what the data about living and working and that commuting patterns knew. And because we knew that, we had a strong inclination that getting that data was going to help us with this problem. So my overall conclusions are, please do not assume that missingness is random in administrative data. It is probably not. And it can also change over time how it's indicated. So always check for things that pop up and are new, or new codes, because it may be somebody's solution to a system that hasn't been designed to do what they needed to. And Frauke talked about that a little bit. The level of missingness that was brought up in several presentations, and Adam, I think you also hit it, in terms of you may not be able to actually report on this thing you would like to, because there may be so much missingness and you're pretty positive it's not random, that it just should be dropped, whether that's, you know, a variable that could not be considered, and you can report on that missingness like Tian talked about. And then if you are going to report, bring in that as much as you can, what you think is the pertinent background information that someone needs to locate this information. And also know that you have options. You can place a restriction on your cohort with a big disclaimer that you may have changed slightly what you're answering about, and it may not generalize well. And there are a lot of cases when you've identified the missingness that additional data does help. So that's the end of my presentation.
Great, thank you so much. I see a common theme here, right? You all mentioned that it really is important to understand that missing data mechanism, right? And we had a little bit of that with the UX for those that enter the data, but obviously there can be other problems of that type. Any questions from the audience? I did see one comment from you, Adam. I don't think that is a question, but it could be one. Do you just want to share what you meant with semi-randomly?
I was just joking because on the first slide, it said, I think the first bullet that was crossed through was like completely, truly, totally random. And then another one just said random. And then there was another one at the bottom that said not random, essentially. So I was like, okay, so the one in the middle must be something like semi-random.
Gotcha. Yeah.
You know, it occurs randomly, but we kind of know what it is.
I agree that this would be a better term. Like,
I was just teasing.
Good. So I encourage the folks to not be shy in asking questions, but I also want to post one, and I'm not sure if this is mostly for you, Caro, or if the others want to chime in, but we have seen from Rod Little and Rebecca Andrich quite some work on using proxy pattern mixture analyses to sort of get at this question, what to do when you have not missing at random and or forms of that type. Can you share a little bit or elaborate a little bit on what this is about, or if this is worthwhile looking into?
yes. So if you have missing not at random data, like in a lot of cases with all the cases with administrative data, and you have a good idea of what the non at random missingness mechanism looks like, maybe from external data or from external information, you can adjust your imputation model to maybe, for example, if you know, okay, with the imputation model that you get from just the observed data, you will always underestimate your income by a certain amount. Then, or in specific cases, then you can adjust this model to reflect your external knowledge. And this is, of course, a possibility, but you have to have a good idea of what your mechanism looks like. So, yeah, if you can make use of something like that, that's a great option. But yeah, that's also a high bar.
It is. So
yeah.
the example that I just posted in the chat is a paper from Rebecca Andrich where she applied this methodology to the Census Household Pulse survey that was run during the COVID pandemic, and a survey that I was involved in, that COVID Trends and Impact survey, or actually Cara and I both were involved in. And there was a clear hypothesis that, you know, folks that maybe weren't so keen on vaccines might not participating in this survey on COVID, and where questions are asked about vaccine taking. And so with that hypothesis, she's, you know, exploring the possibility of adjusting any missing data bias. I haven't read that paper. You see it came out this month, but that's why I thought I should mention it here. But I have seen her present this work, and I'm looking forward to reading it. The method is a bit involved, but it might be helpful, because in many instances, in particular what we discussed early on with the $1 values that essentially are missings, right? You have a clear hypothesis, maybe what the issue is, or in other settings, when you think it is pretty clear what the mechanism could be, then this could be an interesting technique to look into. So, and Rebecca is probably happy for you guys to reach out. Other questions or comments for any of the presenters? I know we've been at it for a long time, so Angie, I have a question for you, actually. So you said that at the beginning this was all overwhelming and lessons learned from, you know, during the workplace. Looking back, what do you think one should learn before getting into this? Like younger Angie, how would she have wanted to be prepared for this?
The biggest component is I tried to hit the pieces I wanted to know at the beginning, but a lot of times it is that looking at it by years is incredibly important. So no matter what you're doing, look at your missingness across time, because it also points you in the direction of there could have been a policy change, or it looks like people are using this information differently than they used to. And so watching things drop off and come back can be really profound. And then making sure you have those strong connections with your agencies who can call people up, because there's information we've untangled and quite literally sat there. And I've found something that looked weird. I've talked to an agency person, they've called up the person who input the data, and they will find out exactly what they intended to do. And that's led to changes in the input mechanism itself, because sometimes there is something that a human wants to do and they can't do it. And so we often say that something we're not celebrated for, but that we do that's very important, is that we provide the information back to agencies that helps the data collected get better. And some of that is by noticing these anomalies, which helps them change the system so that it can handle what people actually need it to handle.
And actually, I would augment that and say that's not just true for missing data. This is actually true for any variable, right? I mean, so the value of like these intensive descriptive analyses of data that we look at by year, as you said, is I think a super important hint that you give there. Jan, any closing words from you for us here in this session? I do want to end us a little early because people between these meetings and the next meetings probably do need a bathroom break at some point. So I'm handing it over to you for a final set of comments or thoughts.
Oh, thank you. So yeah, so I think my takeaway is just it's just very important to understand the missingness, and maybe your tools are very limited. Maybe you don't have additional resources to link with a broader with data set with broader coverage, or you don't really have the proper tool to conduct really good imputation methods. However, I think it's just very important. Sometimes the interpretation of your results are very important. Probably is more important than whatever methodologies that you're using.
Great. Thank you all so much. Thank you for the attendees, for asking questions, for hanging in there, for coming at all. We know now who you are, and if we ever want to talk again about missing data, we will reach out to you. Please reach out to us. If there are further questions, we will post the slides and the notebook and the video on the SoDa website, and hope you engage with the material and with us. And we are looking forward to seeing you in the future. Thank you all.